Hello. In this video, we are going to be looking at the different types of electron domain geometries found in molecules. To do this, we're going to be using balloons to make those geometries. Each balloon is going to represent an electron domain found in the geometry. The first electron domain geometry we're going to look at is the trigonal planar, seen here. There are 3 electron domains found in the trigonal planar geometry. This type of molecule is an AB sub 2 molecule. The number of lone pairs found in this molecule is 1. This lone pair is usually found on the top, so where this balloon would be, which would form a bent molecular geometry. An example of this type of molecule would be sulfur dioxide. The second type of electron domain geometry we're going to be looking at is tetrahedral, seen here. In this geometry, there are 4 electron domains. 1, 2, 3, 4. There are 2 types of molecules in this geometry. The first is AB sub 3, which has 1 lone pair. This lone pair would be located on the top, where this balloon is seen here, and this would form a trigonal pyramidal molecular geometry. An example of this molecule would be ammonia. The second type of geometry, or second type of molecule found in this geometry, would be AB sub 2, which has 2 lone pairs. These lone pairs would be found in the upper 2 corners, like here, which would leave this here, forming a bent molecular geometry. An example of this type of molecule would be water. The next electron domain geometry we'll be looking at is the trigonal bipyramidal, as seen here. It's usually seen like this. It's hard to see all the electron domains like that, so I'm going to turn it around. As you can see, there's 3 going around here, and 1 on top, and 1 on bottom. In this type of geometry, there are 5 electron domains. There are also 3 different types of molecules in this geometry. The first type of molecule would be AB sub 4, which has 1 lone pair. This lone pair would be located on the side, kind of where this balloon is here, leaving these 2 over here and the 2 on the top and the bottom. This would form a seesaw-shaped molecular geometry. An example of this type of molecule would be sulfur tetrafluoride. The second type of molecule in this geometry is AB sub 3, which has 2 lone pairs. These lone pairs would be found where these 2 balloons are located. So that leaves the top balloon, the bottom balloon, and this one on the side. And this forms a T-shaped molecular geometry. An example of this type of molecule would be chlorine trifluoride. And finally, the third type of molecule in this geometry is AB sub 2, which has 3 lone pairs. So those lone pairs would be the 3 balloons in here, leaving the 1 on top and 1 on bottom, forming a linear molecular geometry. And an example of that type of molecule would be iodine difluoride. Now finally, the final electron domain geometry we're going to be looking at is the octahedral, as seen by here. I'm going to do the same thing I did with the other one. You can see the 2 on the top and bottom, and then you have 2 here, and if we go around, we have 2 more, 1, 2. So as you can see, there's kind of 4 surrounding the middle there, and then 1 on top, 1 on bottom. This means that it has 6 electron domains, so the 2 plus the 4 around the sides. And there are 2 types of molecules in this geometry. The first type of molecule is AB sub 5, which has 1 lone pair. This lone pair would be found on the bottom, right here where the balloon is, leaving the top and the 4 around it. And this forms a square pyramidal molecular geometry. An example of this, a molecule of that type of geometry, would be bromine pentafluoride. And finally, the second type of molecule found in this last geometry would be AB sub 4, which has 2 lone pairs. These lone pairs would be found on the top and on the bottom, leaving just these 4 around here. And this forms a square planar molecular geometry. And an example of this type of molecule would be xenon tetrafluoride. So while these show like a general idea of what the molecular or the electron domain geometries would be, they're not exact. You know, the balloons aren't the same size. They're not necessarily the same distance apart, whereas when you look at a typical electron domain geometry, all of the domains would be exactly the same length apart, but this gives us a pretty good idea of what each domain geometry would look like. Thanks for watching.